All right, now we come to the last of our bonding theories, molecular orbital theory. So this is going to be another way of looking at how we explain overlaps and how we explain some of the properties that we see. Once we cover this, we're going to look at oxygen. So what's really interesting is if we draw our Lewis structure for O2, we get this, okay? Now, according to this Lewis structure, everything is paired up. So we should see diamagnetic behavior. There should be no interaction in a magnetic field. But what's interesting is that O2 is actually paramagnetic. And molecular orbital theory is going to let us explain this observation that we see. So let's take a look at what molecular orbital theory is. So we've got our isolated atomic orbitals, all right, where we have our 1s and the number of electrons, and we draw our little arrows. Molecular orbitals are the same thing, except they're going to be considered for the molecule, not just the isolated atoms. We're going to combine our atomic orbitals. We'll get a decrease in energy and some stabilization when we have bonding. We'll get an increase in energy and destabilization when we have antibonding. We fill the same way we fill everything else. We start at the bottom. We put our electron in, we go back in spin pair, put our electron in, spin pair when necessary, moving up as we go. We get something called bond order. So that's going to look at the number of electrons in bonding molecular orbitals minus the electrons in antibonding divided by 2. All right, the way I like to do this is I'll just multiply the whole thing by 1/2. So 1/2 bonding minus antibonding. All right, and that gives us our bond order. Things to think about. When we have our quantum mechanical view of everything, we've got a collection of nuclei that are surrounded by these delocalized molecular orbitals. And so remember when we talked about quantum mechanics and we explored this idea that we can have wave-like behavior as well as particle behavior. And so we get wave functions for our atoms that we sum to get these molecular wave functions. If we get constructive interference, we get bonding. If we get destructive interference, we get antibonding. All right, so this is constructive. All right, and then this one is going to be destructive. Okay, so let's look at these. So here, my bonding orbitals, all right, the waves reinforce. So this is constructive interference. We are adding our wave functions together. Okay, and so we get a region of high electron density between nuclei. All right, so this is constructive interference, okay? Conversely, we get antibonding molecular orbitals. So in this situation, we are subtracting wave functions from each other. All right, and this gives us a region of 0 electron density between nuclei. All right, and so when it cancels, that's where we get that destructive interference. Okay. And so when we start off with our hydrogen, okay, remember hydrogen is just a 1s1. Okay, we get this overlap and then we form or bonding and our antibonding. Our bonding molecular orbital is a sigma 1s. Antibonding is sigma star. So anytime we have bonding, we don't have the star. Anytime we have antibonding, we have that star attached to it. Okay, and so here we get this combination. We combine our atomic orbitals and we get the subtraction to give us our antibonding or our sigma stars, and we get an addition to give us our bonding or just our sigma. Okay, and so we form two molecular orbitals. Okay, so we form two molecular orbitals, one bonding, and that's the sigma 1s, and one antibonding. And that's our sigma star 1s. Okay, and so only atomic orbitals of similar energy are going to interact to give us this molecular orbital situation. Okay, so let's try to fill one of these molecular orbital diagrams in. All right, so remember, hydrogen is a 1s1. All right, so here we're going to have our atomic orbital for hydrogen. Here we'll have our atomic orbital for the other hydrogen. And in the center here, we'll do our molecular orbital for our H2 molecule. All right, so our boxes, the position of them indicate relative energy. So remember that constructive interference, the addition, we drop the energy. That's where we get the sigma 1s. And then our subtraction, where we are getting destructive energy, that destabilizes it, and we bump it up to the sigma star 1s. All right, so I get an electron here and an electron here. So those are my isolated atomic orbitals for each individual hydrogen. So I have two electrons drawn, so now let's fill them in. We're going to start at the bottom and move our way up. I get one electron, two electron. That's it, we're done. There's only two electrons to consider. Okay, we can calculate our bond order. All right. So we're going to get 1/2 of bonding minus antibonding. So I have two bonding electrons minus 0 in the antibonding. So 1/2 of 2 is 1. So our bond order is 1, so we'd expect a single bond, which is indeed what we see. Okay, so a bond order of 1 corresponds to a single bond. A bond order of 2 is a double bond. A bond order of 3 is a triple bond. Okay? I can keep drawing these diagrams, all right? So I can do helium and then a helium with a plus. So my isolated helium is going to be 1s2. A helium cation means it's lost an electron, so that's 1s1. All right, so we'll look at our helium. Okay, so we get 1, 2, 1, 2. So I have a total of 4 electrons that I need to consider. So I'm going to go 1, 2, 3, 4. I fully filled both my sigma and my sigma stars. So let's see here. What is this bond order for this particular molecule here? I'm going to get 1/2 of 2 bonding minus 2 antibonding is 0. Well, bond order of 0 means there is no bond. No bond cannot exist. All right, but what if we have that ion with the +1? So this is our helium. That's our one with the plus. I have to put this above here. Sometimes there's only so much space I have to work with putting my face in the screen here, because I also have to be able to have enough space to write. All right, so there's our helium. There's our helium ion. So I have 3 electrons. 1, 2, 3. Okay, so our bond order We're going to get 1/2 of 2 minus 1 gives us a bond order of 1/2. So technically speaking, this ion could exist. It wouldn't have a very strong bond. It only has a bond order of 1/2, which isn't even like a full single bond. But as long as the bond order is over 2, the molecule can exist. So as long as the bond order is over 0, as long as bond order is greater than 0, molecule can exist. Okay? So as long as it's over 0, it can exist. Whether or not it does exist or would exist very long is a completely different story. But as long as that bond order is over 0, it can exist. All right? So let's take a look at lithium and beryllium. So now we're in period 2, but these are our first 2 elements in period 2. Okay, so lithium is a 1s2 and a 2s1. Now, what do we care about with bonding? Do we care about that 1s orbital anymore? No, because that's core. We only care about the valence. So I only have the 2s shown here because the 2s is what we're going to deal with bonding because that's where our valence electrons lie. Okay? So we'll get lithium, and we'll get our molecule. So I have a single 2s for each of those, and then I have a 1, 2 for that. So our bond order is 1/2 of 2 minus 0, which is 1. So can that lithium molecule exist? Yes, it can. All right, let's take a look at our beryllium. Again, I ran out of space, so I'll put it up here. Okay, so beryllium, we'll move 1 over. We get 1s2, 2s2, and again, all we care about is that 2s. So 1, 2, 1, 2. Total of 4 electrons, so we'll go 1, 2, 3, 4. All right, so our bond order, 1/2 of 2 minus 2 gives me 0. Cannot exist. Okay? All right, so now let's do an exercise here. Let's look at these 2 diatomic hydrogen ions and see if either of those could exist. Okay? So practice what we just did and see if you can fill these in and calculate those bond orders. So try it first. And then let's see if you did it correctly. All right, so we'll do hydrogen, hydrogen plus, and then hydrogen, hydrogen minus. Okay. All right, so hydrogen has that single 1s. My hydrogen plus, well, that means we've taken away an electron, so it doesn't have any electrons, right? That's just a proton. Okay, so we'll fill in our atomic or molecular orbitals, and that's the only electron. Our bond order, we get 1/2 of 1 minus 0 gives us 1/2, so can exist because it's over 0. All right, now this one, our regular hydrogen gets that. Now the hydrogen anion. An anion means we have added electrons. So we'll get that 1 extra electron there. All right, now I have 3 electrons to consider. 1, 2, and 3. So my bond order, 1/2 of 2 minus 1 also gives me 1/2. So this also can exist. Okay? All right. Now, if we go past hydrogen, helium, lithium, beryllium, we move into a region where now we have p orbitals. And so when we move into group 3a of period 2, we have to consider both the s and the p electrons. All right, so we start getting situations with sigma and pi, because remember, I have 3 p orbitals, end-to-end overlap, sigma bond, and then anything else is pi bonds. All right, and so here I get end-to-end sigma molecular orbitals. Okay, and then sigma, sigma star for bonding, anti-bonding. And then when I look at my other p orbitals, I get side to side overlap, and we get 2 pi molecular orbitals. Okay, and we get pi and pi star for bonding and anti-bonding respectively. Now, when we look at the order of the molecular orbital energy, it's based on 2 things. All right, it's based first on the order of the atomic orbital levels, and second on the mode of p orbital combination. And what's interesting is when we look at the other 6 elements in period 2, we see 2 different things happen. All right, we're going to see a situation where the size of the atom allows for mixing between the 2s and the 2p orbitals, and does not allow for mixing between the 2s and the 2p orbitals. All right, so when I look at period 2, all right, our first situation is no 2s, all right, no 2s, 2p mixing. And this is going to be for oxygen, fluorine, and neon. Okay, so for those 3 molecules, our oxygen or fluorine and our neon diatomic molecules, we get no 2s, 2p mixing. So this is the diagram that we see, all right? No mixing there. We go sigma 2p, pi 2p, pi star 2p, sigma star 2p, all right? Okay, now here's what's happening. When I look at these guys are small, all right? So we get small, relatively strong repulsions. Okay, are going to occur as 2p electrons pair up. This raises the energy of 2p orbitals high enough above 2s to minimize mixing. Okay? Now, our other 3. So remember, we get smaller as we go across the periodic table. So our oxygen, our fluorine, our neon are smaller than our boron, our carbon, and our nitrogen. All right, so when we look at boron, carbon, and nitrogen, they're a little bit bigger. And so what we see is this. We see some mixing there. And so you see our pi 2p occurs lower than our sigma 2p. And you can see there's this kind of weird misshapen look to what happens with our sigma 2s and sigma star 2s, all right? And so this has our 2s 2p mixing for our boron, carbon, and nitrogen. Homonuclear diatomics. Homonuclear, remember we're dealing with 2 things that are the same. All right, and so these guys are larger. All right, and so here, when 2p atomic orbitals are half full, repulsions are relatively small. So 2p energies are closer to 2s energies. And actually I'll write out and because it almost looks like a sigma. And mixing occurs, causing pi 2p to appear before sigma 2p. Okay, and so you have to remember which one is which causes the mixing and which does not. Okay, all right, now let's look at some molecular orbitals here. Let's explain what this oxygen thing that I talked about at the beginning was. So there's two electromagnets there. There's some liquid oxygen being poured between those two electromagnets. It suspends, which means it's paramagnetic. This Lewis structure, however, doesn't look paramagnetic. It looks like everything's paired up. All right, and so this seemed impossible to reconcile before molecular orbital theory. So let's look at this magnetic behavior and the bond strength of oxygen as well and see what is occurring. All right, so oxygen, all right, remember oxygen is small, all right, so oxygen, no 2s, 2p mixing. Okay, so now if this is oxygen, and this is O2. All right, my valence on oxygen, I have 1, 2, 2s, and 1, 2, 3, 4, 2p's. Okay, so same thing over here, 1, 2, 1, 2, 3, 4. All right, so for my sigma, my 2s there, I have 4 electrons. 1, 2, 3, 4. Okay, for my 2p, I have 8 electrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Because remember, we put in single ones before we spin pair. Our bond order. 1/2, I have 8 electrons sitting in bonding orbitals. I have 4 electrons sitting in anti-bonding orbitals between my s and my p. So I get 2. So that matches the Lewis structure. All right, and then what do we notice here? I have 2 unpaired electrons in pi star 2p. So explains magnetic behavior. Okay. All right. Now I've got an example problem here. All right. So we've got some data that shows that removing an electron from nitrogen forms an ion with a weaker, longer bond. All right. Whereas oxygen has a shorter, stronger bond. So we want to fill in some diagrams that show the sequence and the occupancy of these molecular orbitals. I am going to give a little bit of information, but I'm going to leave the rest up to you to try. If you are one of my students that it's in one of my lectures, my first semester Gen Chem, this is going to be a challenge problem. Okay, so on the next 2 slides, I've given some blank molecular orbital diagrams for you to fill out. And so your job is to fill them out and then to, calculate bond orders and explain what you are seeing based on what we know about different bonds. Like what is shorter, a double bond or a triple bond? What is stronger, a double bond or a triple bond? And put all this information together to give an explanation. Okay. So these diagrams are for nitrogen, all right, because we do have 2s, 2p mixing. All right, so you'll show the nitrogen that's not an ion, and then you'll show the one that is an ion. Calculate your bond orders and give an explanation. Okay, and then you'll do oxygen. Okay, same thing, oxygen. And you'll do the ion one. Calculate those bond orders and provide an explanation. All right, so this is your challenge problem because I haven't done one of these in a while, in a few chapters. So here's a challenge problem. It's perfectly fine if you print these diagrams and fill them out and do your things there. I've tried to put the blank diagrams. These are a pain in the butt to draw without having them pre-printed. So I've tried to pre-print them for you so that you can just print off these two individual slides with the blank diagrams on them and fill them out directly on the slides. That'll make your life much, much easier. All right, so there's your challenge problem. Now we've looked at homonuclear diatomics. What happens with our heteronuclear diatomics? Well, once we start combining things, we've got a nitrogen, an oxygen, and then a nitrogen monoxide. Once we start combining things that are not the same, we start getting things that kind of go a little bit wonky. Remember, I mentioned that we have to have orbitals of similar energy to get this perfect mixing. Now, even though nitrogen and oxygen are right next to each other, remember nitrogen, it's a little bit bigger than oxygen. So we see that 2s, 2p mixing. Oxygen, we don't see the 2s, 2p mixing. And so when we try to showcase molecular orbitals of this heteronuclear diatomic, we start to get something that differs a little bit from the energy levels, okay? And then when we start looking at things like hydrogen fluoride, where we've got this non-bonding situation because fluorine has more orbitals than hydrogen does, we start to see things deviate even further. So to study molecular orbitals of heteronuclears, there's a lot more considerations that go into it. So that's why we're really just focusing on our homonuclear diatomics through the end of period 2. It gets even crazier once we go past period 2 into period 3, or when we start looking at heteronuclear situations. Okay? When we look at things that have resonance, we've talked about the fact before that we get this delocalization of that electron density. Our Lewis structures, we draw individual situations. And if we look at it from just a valence bond perspective, then it looks like we have a single bond and a double bond. And where does that fit? But if we look at it from a molecular, standpoint, then we start to see that delocalization. We can see even with the valence bond model, we could start to see, oh, hey, if we take into consideration, all the different hybridizations and where everything is, we see that delocalization. We can look at the same thing for benzene. All right, so bonding theories, we finished them.